explain that there were technical difficulties, but they're solved now. That's all that matters. All right.
You were saying.
Same. Okay. I won't jinx it anymore. So I'm just gonna go ahead and introduce. This is Anthony Pullen. He comes to us as an associate professor from NYU. He started his education at Southern University and A&M in Baton Rouge. Then he got his PhD at Caltech in 2011. After that, he was a NASA postdoctoral program fellow at JPL. And then he got the McWilliams Fellowship at the Carnegie Mellon. And he works on developing line intensity mapping measurements, which he uses to study galaxy evolution cosmology. His last year in 2024 for the line intensity mapping conference. And today he's going to talk to us about exploring line intensity mapping. You ready?
I think so. I tried to pin this so you can see me, but
you want me to just
no, I do it this. I think
okay,
this
perfect.
may work, but no, it won't. Okay. Well, I'll just do this. So I'm sorry if the people can't see me on the Zoom, but they can see the screen, so they can see the slides.
Go ahead and get some.
Okay, I'll get started. Good afternoon, everyone. Thank you. First of all, I want to thank Kurt for hosting me, and also too, it's been a really enjoyable time getting to meet the grad students and the postdocs, and got to see some more friends and meet many new ones. But I'm really excited to discuss today work exploring cosmic noon with line intensity mapping. So first, I'll start off by explaining what cosmic noon is, and then I will discuss some of the background for why we want to use line intensity mapping in order to characterize it. And then I'll talk about some results that my group has been working on in order to better explore this epoch of cosmic history. So of course, I wanted to highlight my collaborators who are all listed here: Rachel Somerville, postdocs, former postdoc Patrick, Bryce Bricey, current postdoc and Yvonne Roy, and grad students as well. Let's see this. All right. Yeah. Okay. So first of all, just to start off, we think of the cosmic volume. We think of something like this. So we see this is an image from the Hubble Ultra Deep Field, as produced by the James Webb Space Telescope, which is our latest optical infrared telescope in order to observe the cosmic volume. And so you see many stars here. For the brightest galaxies that we see, most of the galaxies are around redshift 1. But one thing we want to know is, this picture of the universe as we see today, how did the universe get this way? When did the universe start to look like this? Because we know that at the beginning of the universe, the matter was contained in a plasma with baryons coupled to photons. And so somehow we got to this point here. And so when we think of the universe as we see today, again, there's a whole process that, where the cosmic volume transformed into this state. And so one question is, what was the point at which it came to this state? So cosmic noon is the epoch that is the name that we give the epoch in which sort of galaxies became what we see today. So this epoch is about 2 to 3 billion years after the Big Bang, or between redshifts 2 to 3, 2 to 4-ish. This is a period that's characterized by rapid galaxy growth, rapid star formation, as well as production of metals. So once you had multiple generations of stars, you begin to produce heavier elements like carbon. This is also a period for rapid supermassive black hole growth. So, for example, this is the period when we start to develop the supermassive black holes that are at the center that we find at the centers of galaxies, including our own. You also see this if you track the star formation rate. So this is a measurement of this is a collection of measurements from what's known as the star formation rate density, or the number or the mass of stars produced per unit time. And you see here that as you look to the first few billion years of cosmic history, you see this steady increase of stars that is produced, and then around cosmic noon is the point which you had this peak of star formation growth. And so right after this, from here to today, the density of total matter in the universe increases by a factor of 10. over the last 10 billion years. But over this last 10 billion years, the rate of star formation has actually decreased by an order of magnitude. And so the question then is, what causes this period of rapid decrease in the star formation rate? And so we think that this is due to feedback from two sources, both from supernova that expels gas out of star forming regions, choking off the production of star formation, as well as feedback caused by hot gas around supermassive black holes. But how that's actually fully characterized, that's an open question, and so that's the work of astronomers to try to fully understand this period and why star formation rate turned off at the end of this epoch of cosmic new. Okay, so how do we track the extragalactic star formation? So stars form in clouds of molecular hydrogen and dust. It's the dust that allows the regions of molecular hydrogen to cool in order for gas to condense to form stars. Much of the UV optical starlight that is produced by stars, though, is actually absorbed by the dust itself. And so, this energy is then re-emitted in the infrared. So here is a picture of the Eagle Nebula, and these peaks here of gas, these clumps of gas are where stars are formed. So these regions here, and then over here is you can see a full spectrum of emission, where this blue represents what the intrinsic luminosities that you would expect from star formation. And whereas the red, it accounts for the fact that much of the emission is absorbed by dust, and so you see less emission in the UV, and then you see more, and then that emission is then redistributed in the infrared as dust emission. And so actually, you'd want to be able to characterize this full region from the UV all the way to the infrared in order to really understand star formation, and that's why a lot of surveys are working in order to characterize this emission. So and this is also going to be important not only for characterizing star formation, but the emission from supermassive black hole accretion as well. So much work, many surveys are looking at this continuum emission, but also the emission lines also have a role to play here as well in characterizing the processes of star formation and other processes for galaxy evolution. So, for example, you have H1 clouds, which can be tracked using 21 centimeter emission. You have photodissociation regions where stars emit UV light that then ionize the regions around the gas around them, which can then collide with electrons in order to produce C2 emission. You still have traces of molecular clouds. So, for example, while molecular hydrogen doesn't have a permanent dipole, so it's hard to measure. You do have other lines like CO, carbon monoxide, and C1, which tend to trace these regions as well. And then you also have nebular emission from H2 regions with and these are lines such as H alpha, nitrogen 2, oxygen 2, and oxygen 3, and many other lines. And so by measuring all these lines together, I'm not going to go into this talk deep into what all these lines trace, but the main thing to know is that since each of these lines measure different regions of the interstellar medium, you can actually use it to trace different properties, because each of these lines are also going to depend on the different properties of the interstellar medium in different ways. One thing to note, though, as far as how to best track these lines, is that one issue is that most in molecular hydrogen, for example, is outside the brightest galaxies, and in the same way, most of the emission that we can actually observe is not contained only by the brightest galaxies. So here I show a figure just giving the example for molecular hydrogen. This is an analysis that was done by Gregor Popping in 2019, where you take the illustrious TNG simulations and you could mock an observation of aspects, which is an almost complete galaxy survey, where this shows what would actually be detected over the volume simulated by illustrious TNG for the aspects survey, whereas this shows what total emission would be from all the galaxies that exist in the simulation. And so this gap here shows you that there's much emission from much total emission that is not being captured that's tracking H2 molecular hydrogen that's not being captured by the CO that would be measured just from a bright galaxy survey. And so this serves that the main point is that galaxy surveys will not capture most of the emission from molecular hydrogen at early times. And this is also true not just for molecular hydrogen, but for star formation and other processes as well. And so the question then is how do we get this other emission in order to see the full processes of galaxy evolution? And so line intensity mapping is our proposed way to do that. So the main idea is that the way that it works is that you measure the aggregate emission, the aggregate intensity in large 2D pixels, but you measure these in multiple frequency bands. The goal of this is that if you sacrifice basically angular resolution in order to sample the faintest objects. So you do this you perform this measurement in large pixels. You're not able to image individual galaxies. You're not able to detect individual galaxies. But the goal of it is to be able to measure the full emission over cosmic volumes much larger than you can access with galaxy surveys, and over fainter objects that you wouldn't be able to detect using a traditional galaxy survey. So for those who are interested in cosmology, which this will probably be the end of all I talk about in cosmology in this talk. The goal is that you want to be able to map large volumes and then map over much earlier times, and this will be great for measurements of the early universe and also for growing gravitation. But at the same time, by measuring, but at the same time, you will be able to also measure many emission lines, again, over large volumes, over a large range of redshifts. And this will this will be great for probing galaxy evolution because you can track different galaxies over cosmic time for much larger, over a large range of redshifts. And particularly when you have many lines, they can trace, for given an instrument, they will trace a large range of volumes, but also you will be able to understand many processes by being able to measure all these lines. And so to sort of see how this all plays together, you sort of have your galaxy survey. I've decided to plot these three different types of broad categories of surveys over three axes. So this axis tomography denotes how well you can. Yes.
There's a question online from Ryan Fields.
Sure. Yes, Brian?
Oh yeah, Anthony, I'm so sorry. I think you're probably answering it now. So let you finish the slide and see if I still have a question.
Okay. So this axis tomography denotes basically how well we can measure, how well we can measure the maps precisely in redshift if you're sampling the 3D volume. This axis depth measures how faint can we detect the emission from galaxies, and then this axis quality measures how well we can resolve galaxies in order to be able to do galaxy imaging. So galaxy surveys are really optimized in order to be able to measure, for the quality axes, and that you can image individual galaxies and see the different components of those galaxies, as well as if you have the spectra, you can use the lines in those spectra in order to be able to track where galaxies are along the line of sight in redshift. And extragalactic background surveys, so these would be surveys like surveys of the cosmic infrared background, or surveys like, or even surveys like the cosmic infrared background, the cosmic optical background. These are different types of surveys that measure the diffuse emission. These surveys don't measure, they don't have quality, and these surveys also don't resolve individual galaxies, but they have very high depth because the continuum emissions of these galaxies are usually really intense, and so you can measure these. You can sample galaxies for very high depth. However, it has no ability to resolve tomography because these extragalactic background surveys measure the continuum emission of galaxies, and so you can't, and so it doesn't give you any information along the line of sight for where the galaxies are that are being contributing to your signal. Line intensity mapping, on the other hand, they're not quite as complete. They don't have quite the same depth as line intensity as a extragalactic background surveys, just because the total light coming from the lines are fainter than the light that's contained in the continuum. However, and they're not optimized for quality because again, you're not resolving individual galaxies, but they are optimized for tomography such that a line intensity mapping survey would be able to produce potentially a 3D map of cosmic structure and it'll allow you to track galaxy evolution across cosmic time. Any questions so far? Hey Brian, did I answer your question?
Yeah, more or less. So is the idea then that for line intensity mapping you want like sort of spectral resolution and field of view at the price of less angular resolution?
Yeah, that's correct.
Got it.
With different line intensity mapping surveys having more or less spectral resolution, but generally you want high enough spectral resolution so that you can resolve along the line of sight.
Right. Fair enough. Cool. Thanks.
Anthony, could you raise your volume just a little bit?
Oh, sure.
Or so to the owl. Oh, yeah, it's fine.
Oh, it would have to be, it's on that second. Yeah, it's not on my.
Maybe just repeat the questions when you ask.
Yeah, I'll repeat the questions. Right. Go ahead.
All right. Here's just some quick examples of some measurements that have been done so far. So, well, first of all, on the left-hand side, you see some maps of different surveys that are in different stages of either being proposed or operating. This is a graphic produced by my former postdoc Patrick Pricey, whose work I'm going to actually feature later in the talk. And so you could see some ones I want to highlight are a CO map, which is located here, which has done these measurements so far of this different stacking analyses different stacking analyses to try to measure the first rotational line for carbon monoxide stacked off of quasars. I also of course want to highlight TIM, which many of you are involved in here, and then so it's exciting seeing the progress you all have made, and I'm hopeful that I'll be seeing data from you guys in a couple of years, and so I'm really excited for that. I also wanted to highlight SphereX, which is a survey that just launched in February and starting science operations in May. That will and so this will track lines like H alpha and O3 as well, and so this will be useful for this could be useful for training star formation as well. And yeah, so I also wanted to highlight Lyman alpha intensity mapping that has been done by the HEDDEX collaboration as well, which they've made some stacking analysis using both their galaxy data and their diffuse emission data. Okay, now here I want to highlight just the common sort of line intensity mapping science pipeline that you should keep in mind. So you start off with, you have some line intensity mapping. Notice one thing that I didn't make explicit is the fact that these line intensity maps need to be clean from foregrounds, which could be its own talk, how to do that confidently. But once you have those line intensity maps, then you want to construct some statistics with it, because since you're not measuring individual galaxies, you can only do statistical measurements using the full maps in order to sample the large scale structure. And then, of course, another thing you need is the statistics model, which combine knowledge of the galaxy evolution as well as cosmology. And by putting these two together, you do some kind of inference. So that could be either some kind of parameterized model, where then you perform a Monte Carlo Markov chain, or you can use machine learning or some combination maybe. And then finally, your output is you want some knowledge of galaxy evolution and cosmology. So first of all, much innovative work has been done on designing pipelines for processing line intensity maps and various statistics that can be used in order to get at the science for these maps. So much innovative work has been done. Cosmology clustering model, I believe, at least the first order cosmology clustering, that's been settled. We know what the power spectrum, at least on linear scales, looks like, and so we know how to this is known how to use. So this is basically at least the first order is basically a solved problem. But what work is really necessary is really modeling galaxy evolution. So being able to, first of all, know how galaxies evolve over time, and then connect those to emission signatures. It's a really hard problem. It's much work is being done, and that's sort of what I find myself in, is being able to, in order to use line intensity mapping to its full potential, we need to know how galaxy evolution. At least need to have some idea at least how to characterize galaxy evolution in our model so that we can do inference. So the rest of my talk is going to go as follows. First, I'm gonna start by I'm gonna take a side detour to talk about a recent CO measurement that my postdoc did using doing a stacking analysis. And then the rest of my talk will really be about, the bulk of my talk will really be about different inference tools that we've been developing in our group in order to try to in order to hope to build a pipeline for doing future line intensity mapping measurements of galaxy evolution. And then finally, assuming I have some time left, which we started late, so I probably won't, but I'll highlight some future work that we're doing. All right, so so I just wanted to have, this is work that was completed by Dr. Aaron Rohr, my postdoc, where he stacked Planck CO maps on EBOS galaxies in order to try to detect the third CO line, CO382. So he stacked 400,000 galaxies per redshift bin, where the galaxies were divided in these 4 redshift bins. Okay, and using galaxies from the EBOS survey. So EBOS is the 3rd generation Sloan Digital Sky survey. We're over it, and we used basically the luminous red galaxy sample. So these so we use a 10-degree aperture for this stacking analysis, sampling. And so in order to get the noise signal, we actually sampled not just in the middle or where we line the galaxies to stack, but we also sampled outside in order to get an idea of their full noise and characterize the noise. And so basically what we find is that we seem to find some signal by sampling and so basically these are the same maps. This is sort of the same map but stacked on different galaxies. So and so when we find is that we basically find that when we stack on these other redshift galaxies with these other redshift range, we either get no signal or something that looks like a cosmic infrared background. But for this one, we seem to get something separate that could be signal. And so then by using the stacking, we're able to we make this plot where we're able to sample the full intensity by just modeling the full sensitivity as a power law. And what we find is that well, first of all, we measure these intensities using the stacking, and we get these results. Whereas the intensity for most of the bins can be just described by this power law of intensity that would be consistent with cosmic infrared background emission. However, we get this excess at this emission associated with this redshift range. And we find that this would be consistent with an expectation for CO emission. If we look here, this work sort of lines up with this model, these different models of emission, where these papers describe the connection between luminosity and the star formation rate, and these align with different predictions of the star formation rate, these different dots here. And so these bars representing the uncertainty given the range of possible star formation rates. And so this looks to be sort of on the in the right area, right level. And so this gives us some evidence that this could potentially be CO excess. We're not confident enough to say that this is a definitive a definitive detection, just because there's some uncertainty in the CO in the cosmic infrared background. But I believe as we are able to do better analysis in the future, where we can really resolve out the continuum signal, we could be on more firm footing eventually to promote this as a particular detection of CO. And in one case, this is a precursor eventually for future stacking analysis, possibly with a CO map stacked on the hectex galaxies or DESI galaxies from the Lyman alpha force. And this would be at redshift 3, which would be more in the range of cosmic new, redshifts 2 to 3. And so this was exciting to see this, see this analysis, and but more work needs to be done. Yes.
How does that compare to the chain model that just came out?
Right. So you mean this model? Sorry, which model?
Equan's Nature paper, the model that came out a month ago.
Yeah. So I think this is consistent. This is definitely more consistent with the CO the CO models. This is not similar to the this is consistent with these models. So yeah, I think I haven't compared these directly, but since these are pretty consistent with these other models in the literature, I think his models were also consistent with models in the literature. So well, at least for the yeah, for CO. So I would imagine it'll also be similar. Any other questions? All right. All right, now let's get to the bulk of my talk, which is about Lyman alpha inference tools. Okay, so first up, in order to do these inferences, because galaxy evolution is complicated, much of the work that I align myself with is using simulations in order to characterize galaxy evolution. So in order to do that, I need to introduce the models we're using. So we use what's called the Santa Cruz semi-analytic model, which is a model developed by Rachel Somerville at the Flatiron Institute. And so the way the model works is that it uses a semi-analytic model in order to paint galaxies and with by modeling the dynamics of star formation as it affects molecular clouds, we're able to model how stars are formed inside galaxies. And also too, by using a sub-millimeter, what's going on, a model called despotic, we're able to also predict the emissions of lines like CO, of lines like CO and C2 as well, in order to which we can then use in order to simulate line intensity maps. So one thing my former student Sheng-Shi Yang was able to do was show that the line luminosities predicted we're well in line with these. Well, this axis is line luminosity, and this axis is the star formation rate. She was able to show that the line luminosities predicted are consistent with measurements from aspects in cold Z data, which are shown here. But the idea is that with the simulations, we can actually predict the line. We can actually predict what the line luminosities could be at much fainter galaxies. And the thing to grab from this is that we're not supposed to believe that this is the right model for galaxy evolution. That's not the point of this. The point of this is to say, this is what it could be. With different assumptions, these models would be different. And so the question is, can we use this in order to can we use this in order to learn more about the galaxies? Which would, because you can change the assumptions in the simulation and it would affect it. But the whole point is, can we use the data themselves in order to discriminate between different assumptions that undergird this galaxy evolution model? The pathway for how these are produced is you start off with, it runs on an in-body simulation where darker matter halos are identified or previously, and then the Santa Cruz SAM, what it does is it basically predicts what the galaxies are, the molecular gas that's produced in there, and how that molecular gas evolves under star formation. And then the next part of it, this is called what we call the sub-millimeter SAM. It then predicts what the line emissions are. All right. So then, how is this characterized? So much of the work that's been done with galaxy surveys, you basically have you have these bright galaxies, and you measure the full spectra, and you use that spectra to characterize the emission. However, for line intensity mapping, we don't have that luxury because we aren't measuring individual galaxies. So instead, what we have to do is instead of analyzing individual galaxies, we need to try to extract the full population of galaxy properties. In other words, if we're going to do galaxy evolution, we're not going to say this galaxy here as this star formation rate, and this galaxy here as this metallicity. What we want to do is we want to be able to say, for all the galaxies that exist, what star formation rates exist, what metallicities exist, how are those quantities even correlated. That would give us some information about how galaxies evolve over time. And so the way we do this is that we can actually take one average quantity that we can use that would well characterize the types of things we want to measure, are things like the luminosity mass relation for particular lines. And one useful idea is to split this into these two components. Okay, so if we were to take all the full population of galaxy properties, where this G is a vector containing all the galaxy properties we'd be interested in, properties like the star formation rate, autometallicity, or stellar mass, other properties like that. You can imagine that the total luminosity average for a particular mass could be written as some distribution of the luminosities given the galaxy properties, marginalized over a full distribution of properties. Okay, so you can sort of think of it as, if I have all these galaxies, if I were to know all the properties of these galaxies, I could then and I knew what the line, then I could, if I knew this function, I would then know what all those what the emission line luminosities for all those galaxies are, and I can combine all that information together to get a full luminosity, let's say, given a halo of mass m. And so a dark matter halo of mass m that's hosting the galaxies. And so the goal of this is to say, well, maybe the thing we actually want to know for characterizing galaxy evolution is this quantity here, which we call the conditional galaxy property distribution. And what it does is it characterizes, given a halo of mass m at redshift z, what galaxy properties could be produced on a galaxy hosted by this halo. But the other piece of information you need to know we call the line luminosity relation. And this tells us, given a set of galaxy properties, what will be the luminosities for the lines that are associated with that galaxy. Okay. Now, this is a quantity that I predicted, and this is not a directly measurable quantity, but it turns out that other quantities that are directly measurable can be written as convolutions of these different functions. So, for example, the luminosity function, which is something that's well measured in galaxy surveys, is a quantity that can be predicted in terms of these quantities if they're known. Another type of quantity is if you measure the intensity. So if you take a map and if you're somehow able to measure the average intensity, but more likely if you measure, for example, the power spectrum, the power spectrum, it will also depend on these quantities as well. And so basically any of your observables can be we show that in our paper that all these observables can be predicted in terms of these quantities. And so plus some clustering model for matter. And so with this, then the goal is that if we can somehow characterize this in some way, then we can maybe we have some hope of being able to measure this distribution, and then those will tell us some new information about star formation that we can measure from line intensity mapping. And so really we feel that this can be an accurate way in order to characterize galaxy evolution from line intensity mapping surveys, is to build this type of a model. So first off, do we have any idea of what this distribution even looks like? Well, we have simulations, so we can use simulations to get some idea of what this distribution could look like. Previous work that was done by my former graduate student, Dr. Yucheng Zhang, who's now a postdoc at Tsinghua University in China, was able to characterize this distribution for various galaxy properties. So here is listed 5 properties that fully characterize the emission spectrum of galaxies in our simulation: the stellar mass, the molecular hydrogen mass, galaxy sizes, metallicities, gas metallicities, and star formation rates. We were able to construct this distribution just using the galaxies, and he was able to construct it using the galaxy distribution. And we characterize this over a redshift range of 0 to 10, as well as host halo masses from 10 to the 10 to 10 to the 13. So we used about 1 million halos when in this simulation. And then what he's found is that, well, you wouldn't want to use this distribution directly because these are just a bunch of points. But what you can do is characterize them using Gaussian mixture models. So this is a way that you can characterize the distribution that's non-Gaussian by modeling it as a sum of Gaussians. And so we found that two-component a two-component Gaussian mixture model, which is represented by the green curves here, really sufficiently characterize this enough for the observables that we care to use. So for example, here are some examples of different quantities that we could simulate in terms of these components. And so the blue line represents the actual simulation, whereas the orange line represents if you just model the distribution as a multivariate Gaussian, versus the green curve is what you get if you model as a two-component Gaussian. And so what we find, and so in our paper, what we find is that well, visually the one component is pretty good. The two component is best to get it. If you want to get errors on order of 1% for quantities such as the star formation rate density here, the star formation rate function, which is plotted here, which is sort of like a luminosity function, except it's a distribution of star formation rates. And then finally here you see we map here a correlation of stellar masses given the star formation rate, which is a quantity that's often used in analyzing galaxy evolution. And so what we find here is that the two component model does a really good job of characterizing this distribution. You see how the two component model is able to find these two peaks here.
What?
Oh yeah, sorry.
Why does the star formation rate function look so much different than a luminosity function?
Well, you do have multiple. It's a good question. You do have multiple populations that exist here, and this wouldn't be captured by the different lines that you're trying to track for a luminosity function. And so you do have this difference here. Note one thing is that the error bars that the luminosities that are often characterized here, you wouldn't be able to resolve this that well in a real luminosity function anyway, because there's so few objects, whereas for a simulation, we can resolve it. And so we can see effects like this that you may not be able to see in a luminosity function. In a measured luminosity function. Any other questions? One interesting thing that we wanted to see is, well, okay, that was one simulation, but what if you looked at another simulation? Because again, we're not accepting our simulated model as the truth. And so we actually repeated a large portion of this analysis for illustrious T and G. And did we find that they gave the same distributions? No. You see here, you see here that the two distributions are actually very different for these different models, and that's great. Because that means that the distributions, are different, and so you're not having a situation where two different sets of assumptions, sort of get you to the same result. And so the hope is that, can we measure these differences in data and be able to see which is more consistent with the observations? And so that's a goal that we want to see. And so we do definitely see that this could open up a new window in appropriate galaxy evolution. Yes.
So the illustrious TNG was made with a repo, but what were the SEMs made with? Or what is the difference in the feedback model between the simulations that were used between the SEM and illustrious TNG?
It's a good question. So the SEM was not trained on. So part of it is calibrated with based off of bright galaxy data. So it wasn't trained on simulations. I believe a repo was. Yeah, I would have to get back to you on if you. Yeah, so I mean, the way it was modeled was you did have the UV was modeled, and then and then you have the molecular clouds that are split into different concentric spheres, the UV was then modeled how the UV heated each sphere, which would disrupt star formation. But then there were also things that wasn't heated as much would then be allowed to cool in order to collapse and form stars. Thank you. Yes.
What made you pick a two-component Gaussian mixture model? Like, who's to say that, if you expand to even more components, that you see different results, or if you don't use Gaussian mixture models at all, that the results change? Like,
that's right. So that's good. So in principle, basically, we wanted to limit the number of we'd imagine in an actual analysis if we were gonna try to fit for these distributions, you'd want to not use more, you wouldn't want to overfit by using more components than are necessary. And so we found that 2 components was enough to get within 1%, which should be enough for the upcoming, for upcoming, probably over the next 10 years, that should be sufficient for the sensitivity of line intensity mapping surveys that we will, which we would imagine, which we would detect. And note that that's not based on a hard analysis. That's just roughly in my head what I would expect, given you can say I expect measurements on order of 10% or 10% sensitivity at best for line intensity mapping. And so but you can imagine that in the future, as the measurements get better, you may need more components. And so although at that point then the sensitivity would be well enough to where it wouldn't be overfitting anymore, because more components would give you better signal. And then of course at some point Gaussian mixture model wouldn't necessarily be the only way to go. As the sensitivity gets better, then you could consider using machine learning methods as well. And so this was just our first pass of what was something that could be done, particularly with the level of sensitivity that we perceive for the next 10 to 15 years. Any other question? Okay. Now, now if you're actually going to try to measure this, if you're actually going to try to make inference of galaxy properties, given line intensity mapping, there's sort of 2 paths you can follow. Starting off with the line intensity mapping data. So one path is to say, well, I know, I want to let's say I just want to measure the star formation rate. I just want to measure that over cosmic time. Okay. You may say, well, I have some line that I know varies with the star, luminosity varies with the star formation rate. Okay. And that's all I know. What you can do is you can say, oh, well, I have this information. And so therefore, if I measure line intensity mapping and measure the intensity, it should be related to the distribution of star formation rates. And so then I could sort of sample that measurement in order to get star formation rate as a function of mass and redshift. That's the best I could hope for. So that's one path. Another path is to say, well, actually, I have this model here that predicts the luminosities, not just in terms of the star formation rate, but in terms of many other galaxy properties. Then in that case, then you may want to use this information in order to then sample over multiple masses in order to actually characterize this function, this galaxy property distribution, as a function of mass and redshift. So these are the 2 pathways you can follow for line intensity mapping inference. I will say that most of the inferences that have been done in the past have mainly followed a version of this model, although it's a very crude version. And so what I'm going to do for basically the rest of the talk is to sort of characterize, okay, this is to start the conversation, which I won't finish, but I'll start the conversation of how we can actually use this measurement this method in a more responsible way. And then I will discuss sort of the beginnings of how can we actually use this method as well. So this work, so for the first method, this is work that was done by my graduate student, Aiden Subramovic. And what they did was, what they did was what we wanted to consider was, if we had some an intensity map of ionized carbon, or C2, how will we use it in order to constrain star formation, the star formation rate? And so it is well known that the star from galaxy measurements that the star formation rate is correlated with is C2 line luminosities. But we know that it's also correlated with other properties like metallicity. And so one consequence of that is that if you were actually take our simulation and look at how the luminosities are correlated with the star formation rate, you can see that depending on the mass of the host halo, the relation is actually different. What these lines represent is our luminosities SFR relations for different models. So what's funny is that in galaxy surveys, normally this is assumed as a 1-to-1 relation, whereas what we actually find in simulations, if if you simulate lower mass halos, you actually find that this is a relation that depends on the mass range of the halos you're considering. And so you know, and so this is an issue that usually is not taken up. So in prior measurements, for example, in trying to measure the molecular hydrogen distribution given CO measurements, usually it is also assumed as a one-to-one relation, but we suspect that that relation could also be mass dependent. But anyway, let's focus on this. So each of these lines are actually a polynomial fit of the so if you take an of the power law for a line luminosity SFR relation, and again you see that for different masses, with the masses ranging from 10 to the 9 to 10 to the 13, with different mass bands, you see that the lower masses you get it's here, whereas the higher masses the relation is more up here. And this is true for various redshifts. You see that there's sort of collapse. And you also see these spurs, which are different populations of which you can sort of morphologically see as different populations. But what you definitely see is that for line intensity mapping, this is something that you would want to consider, is that this if you want to just take your line intensity maps and try to use those to create star formation, you need to take this variation into account. And the reason why you have this difference is really as a result of the distribution. Because since if the luminosity is only dependent on the star formation rate, we wouldn't expect this to vary with mass, halo host mass. However, because it depends on other properties, those other properties, the distribution of those other properties do depend on halo mass. And so when you marginalize over all the other properties, which is effectively what you're doing, when you find a luminosity SFR relation, that's when you're going to get this dependence on mass. It's because of that marginalization over other properties that aren't being accounted for. Okay, and so if you're going to stick with this, you should take this into account. Okay, so what we do actually is another thing we found. So what we actually do is we did develop this model, and then we tried to see by being able to use this doing a polynomial fit, how well are we able to produce observables? And so one thing we find is that if we're able to predict a luminosity function given the SAM versus this model that we made, which is the orange curve, we do see that they tend to match pretty nicely. We do see a slight difference here at redshift 5 at these very large luminosities. These wouldn't, although most of the signal would be dominated, at least for the line intensity mapping signal, by these lower luminosity galaxies. So this would more affect a bright galaxy survey measurement than a line intensity mapping measurement. But we do see, for the most part, that it looks pretty similar. To see more quantitatively, two properties of the luminosity function that we would want to definitely characterize for line intensity mapping measurements are the first and second moments. The first moment you can think of sort of as an average luminosity, and that directly affects any measurements of the intensity. Whereas the second of C2 and the second moment is a good characterized of what's known as a shot noise, which is the Poisson noise resulting from just the emitters being accountable. And so because of that, we definitely want to characterize, because these two moments will directly affect any interpretation of a power spectrum measurement, for example. So what we see here is these actually do pretty well, believably not. The fractional error is within 5% for the first moment, and well within 20% for the second moment, which should be good for at least the current generation of surveys. If your measurement is not going to be greater than 5 sigma, for example, this should be pretty good. And this is over a very large redshift range from 1 to 9. And so this should, so for Pathfinder line intensity mapping surveys, this should be good enough. And doing it this way is a better way than what's traditionally done, in that you're accounting for the halo mass dependence. And so the next stage of this project, so this will be a paper that we hope to publish at least for the next few months. And then the next next stage of this will then be to characterize how sensitive a measurement done this way would be to the simulation that you're assuming in order to make this model. Because one drawback of this model is that you need to simulate this luminosity SFR relation. And so the question is, how sensitive would our any measurements of this star formation rate distribution be given that assumption? And so that's the next stage to find out how sensitive that really is. And the second path, oh yes. So I'm going to end with this. The second path is to say, well, what instead of assuming just a one-dimensional model of the luminosity given one property, what would we consider all the properties? And so in order to go for that, the first thing we want to do is to be able to build a model that relates the luminosity to all the different galaxy properties. We could do this directly with the SAM, but even though the SAM is the simulating model is much faster than doing a hydrodynamic simulation, it's still not fast enough, particularly if you wanted to do a Monte Carlo Markov chain analysis. And so in order to get around this, my former postdoc, Patrick Brycey, who's now a professor at Southern Methodist University near Dallas, what he did was he actually built a Gaussian processing simulator. And so this is a machine learning method where he took this the SAM data and and with the galaxies and with the luminosities already simulated, and then tried to construct an emulator that predict those luminosities well. And so we were able to and so he set some benchmarks, and what we were able to find was that we were able to using by using a training sample of about 100,000 about 100,000 halos over a redshift range of 0 to 9. What he was able to get was an emulator that was with 10% accurate in log luminosity for all the galaxies. And it's actually around 1% accurate for realistic galaxies, because the whole parameter space is actually not well populated, because there are correlations between the different properties. Like, for example, you're not going to have a galaxy with very high star formation mass but low star formation rate. And so for those, you get more of 1% errors. And these are over lines of C2 as well as CO 1 to 0 all the way to 3 to all the way to 4 to 3. And so here are some predictions. Here's some measurements of simulations of the luminosity function, and you see that it does even better than the previous method. And what we find is that for the and it's much faster. It's 1,000 times faster than the sub-millimeter SAM. It's actually, with each galaxy taking only 10 microseconds to simulate the luminosity. And so for this, and so with this, you're able to, and also there's a 10% accuracy for the moments of the luminosity function. So whereas earlier the second moment was around 20% accuracy, now this gets it to 10% accuracy. And one nice thing to note is that this was all trained on a laptop. So this was trained just using a laptop, and so that was so this is run on a laptop trained on CPUs. And so we wanted to use as minimal computing power as possible, and we're still got an emulator that should be within the needs we would need for sort of next generation surveys, which we hope would be able to reach the 10 sigma level of accuracy or precision. So one thing we wanted to see was, okay, giving our model, we'll be able to see some difference if the distribution of galaxy properties change. And so taking this distribution of galaxy properties here, what we see was if we shifted the means of these points, we see that we definitely, for each property, we do see a shift in the at least for most of the properties, we see a large shift in the luminosity function by shifting this distribution of galaxy properties. And so that means that for anything that we measure that would be correlated with this luminosity function, like a power spectrum, for example, we should be able, there is a hint that we measuring those would be able to discriminate different measurements, different predictions for what this distribution could be. And so the hope is that we could that this will be a toolkit for being able to characterize the properties of galaxies in the future measurement. So next stage things that we want to do. So first of all, we feel that we can make this this emulator even more accurate if we were to train using more more halos. But in order to do that, we need to use GPUs instead of CPUs. So right now, Patrick has a student who's working on setting this up to train on GPUs. And the second thing we want to do is then instead of setting this hint, we want to actually do a full pipeline simulation of an analysis where we would actually characterize this distribution given some expected line luminosity, line intensity mapping data. And so my postdoc at Aurora is currently working on this project now in order to see how well that could be characterized. So I think I'm out of time, so I won't have time to go over these works. I think I've talked with a lot of you about the spheric stuff anyway, so we can move on. And so I'll just leave it at the summary. Just to say that, cosmic noon observations, I hope I'm motivated that cosmic noon observations are important for revealing galaxy properties at the time when the universe seemed to look like started to look like it does today. Line intensity mapping does have the potential in this epoch to be able to characterize this epoch by going after the faint galaxies that won't be observed by a bright galaxy survey. And so our group has focused on developing toolkits for be able to analyze this data in a responsible manner, line intensity mapping data in order to probe galaxy evolution. So thank you for your attention, and I'm happy to answer that.
So, you're using kilometers as one of the basic parameters in this modeling process. I wonder if you, what if you consider stellar mass, which is something that you can measure for individual galaxies?
Right. So stellar mass is one of the properties that is included in the galaxy property distribution function. So it's considered along with other galaxy properties like the star formation rate, metallicities, and other properties. So that's considered as one of the properties for the distribution that we would want to measure. The idea being is that those distribution of properties should be correlated with the halo with the halo mass because depending on about the size of the host halo that's hosted in mass, the simulations seem to show that there are correlations in the galaxy properties. And this is knowing very little about how the actual galaxies evolved. And so sort of you have a situation where we don't necessarily need to know the processes. We're just trying to basically find these correlations. And so then once we can measure them, and this should give us some information where we can go back to the simulations and see, okay, what is the best way to predict these correlations that we see in a way that's not connected directly to the line maps, which has a lot of redundancies, but going back to the actual.
So a quick follow-up on this is that you have this discovered the dependence of star formation rate at different halo masses, right? But there's also this star forming main sequence that correlates between star formation rate and stellar mass. And there's also the stellar mass halo mass correlation. So is the finding consistent with combining the main sequence of star formation and the stellar mass halo mass relation?
Right. So it includes main sequence and starburst galaxies. I mean, one thing in this, for example, is that this galaxy distribution would include any correlations between, for example, star formation rate is here and stellar mass is here. And so these types of correlations would be included in the distribution. And so the idea is that we're not predicting why it's correlated this way. That's not what we're doing. What we're doing is just saying, okay, based off the simulations, we do see these correlations. Then the question is, can data also see these correlations as well? Thank you.
Any other question?
Can you go back to the slide where you have clustering and chip noise?
Sorry, what?
Clustering and chip noise?
Oh, so I had, you mean this slide?
Yeah.
Yeah.
I was wondering if, because you are able to predict the shock noise this well, is it something you can use to construct the model, the shock noise?
Yeah, so the idea is that So the luminosities here, the idea is that if you were to have, the goal would be is if you were to able to measure the power spectrum, for example, and this isn't the only statistics you can use with this. There's other statistics like the volatile intensity distribution. But if you're just using the power spectrum, the goal is the idea is you would have this moment and this moment.
At this moment, it's a bit easier to get data we have now.
Yeah, so this is easy to get depending on for most of the line intensity map, so like for CO map and for others, yeah, usually the shot noise is better, particularly when you have these very small areas when you're not sampling clustering. And so yeah, this is easy to get. And so you in principle you could use this because this would depend on the luminosity. It depends on the luminosity squared. And so if you have a model, if you have, this model, for example, you can use those to substitute. If we basically are providing a a model, a parameterized model for this relation that would then go to predicting the shot noise. One other component that's necessary as well is that because the luminosity depends on other properties, this also produces a scatter. You have this scatter in because the relation between luminosity, even the relation between luminosity and star formation rate and halo mass, even that's not a 1-to-1 relation or 2-to-1 relation, I guess. There is scatter, and because of the other properties that affect the luminosity. And so what we do is we actually fit a model for the scatter as well. A couple of things we find is that it's well approximated by a Gaussian distribution, a log normal distribution. And then so we can use that scatter in order to include it. And particularly for the shot noise, that scatter must be included. And actually also because it's a log normal distribution, it needs to be included in here, but it definitely needs to be included here in order to get an accurate model. Does that answer your question?
Okay, I think we're at the top of the hour about, so I encourage anybody who has any more burning questions to please come to dinner. We're going to dinner at 6. But for now, let's give another round of applause.